Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. We are recording. Christopher, we're recording, man. It's been a while.
I know. I feel like I haven't done this in a long time. I'm a little nervous.
I know.
Not
yeah.
really. I'm not nervous.
No, you're not nervous. Of course not. What's up, man? It's been a bit. You've come back. Well, before we get into it, we're back, I guess, doing regular recordings. We recorded a bunch as we've done the last couple summers. Especially you went everywhere this summer. You were gone for most of the summer. And so we pre-recorded a bunch of stuff, and now we're back. This is August 11 we're recording this, and this will come out the same week. So that's the first time this has happened in a while.
I know. Yeah, we front end loaded this for we did this back in May, right? I mean, we just jammed them and crammed them in, and now here we are, back to the old grind.
Yeah, that's right. So you, Chris, you went on summer science, and we'll talk about that later, but mainly it was Iceland. You just got back from Iceland recently. That was the big trip of the summer in the Bolhuis household. How'd it go?
It was amazing. We were there. Well, we ended up being there for over 3 weeks, but that was because getting back was a bit of a nightmare. Canceled flights and Hurricane Debbie played a role in that whole situation. So that was a struggle. But Iceland was unbelievable. There were things that I saw that were really just humbling for me, and sometimes even like emotional. I don't know, the diversity of geologic things that I was exposed to was just amazing. We did get beat up by the weather, though.
Let me interrupt you real quick there. Were these things that you were, amazed by, are they mostly geological things, or were they other natural phenomenon or cultural things? Like, what were the...
Yeah, that's a good point. All of the above, I guess. What I was referring to specifically, though, was the geologic things that I'd seen. I saw glaciers that I've never seen glaciers of that magnitude. I mean, they were just so big, so thick. I've never seen that. I've only seen pathetic little remnants that you get like in the Western Rockies or the Northern Rockies, like in Glacier National Park, but they're really kind of sad.
Yeah.
And
no, that's right.
These glaciers were not sad. I mean, they were full on just awe-inspiring. I mean, the blue of the ice was just... That's one thing that jumps to mind, and then seeing the calved off sections as the glacier pushes into the lagoon and they break off. And so I've never seen stuff like that before. That's what I was referring to specifically.
That's a very, I've never been to Iceland. I mean, we talked about this before in our sort of intro to Iceland. I've never been, but it's hallowed ground for geologists for many reasons, because it's so unique, both tectonically. It has this tectonically totally unique setting, lots of volcanoes, so the volcanologists love it, and some unique volcanoes. And then it also sits in the northern latitude, so you get this sort of amazing ice sculpted landscape and lots of interactions between volcanoes and glaciers, which is a very unique place on Earth to get that interaction. That's not a typical interaction, so it's a interesting one to study from that point of view too. So yeah, well, it's awesome. I mean, it's a very, very cool place, I'd imagine, to go and spend 3 weeks of camping.
Yeah, not all of it was camping, but like the first week was for sure, because we hiked the Lagavegr Trail, and I'm just gonna say the weather was the real deal. We had it was cold, it was raining, it was windy, and that's not always a good combination, and that happened every single day. But then during the same day, we would get little splashes of sun, and I'd see my shadow. I'd be like, "What the heck is that? I think I see my shadow." It
so
was
good.
But the weather was the real deal, and I guess this summer is the worst that it's been in a very long time.
Oh, you picked a good time to go. Nice.
Yeah.
Perfect.
Of course. That's what I do.
Yeah.
That's right.
Perfect.
And that, what we saw in Iceland is kind of what gave me the idea to pitch to you. Jenny and I saw so many columnar jointing structures in mostly basaltic flows that, Jesse, it was everywhere. And it was one of the coolest things because they weren't the same. I mean, they all looked so different. The sizes of the columns, the geometry of the columns, it was just a spectacular thing. And as I'm looking at these features, I looked at it from the perspective of what do people think when they look at this that don't have a deep geology background?
Oh, okay.
What's going on in their heads?
Yeah.
And that's kind of the angle that I took when I pitched it to you a couple days ago.
So I mean, it's a great. We've kind of briefly touched on this, I think, before, but not really in detail. We haven't dove deep into the columnar jointing phenomenon. So we'll discuss that a little bit, and that'll be kind of that's centering our episode here today. But before we get to that, thanks for listening to this podcast, first of all. And if you're looking for ways to support us, there's one big one we would ask of you at the moment, which is go to our Camp Geo app, download the mobile app. There's a first link in your show notes. You can just click on that, download the app, and give us a review and a rating there. That would really help us. We have tons of free content there as well. Listening to the intro to geology is free, many dozens of hours of content, lots of episodes with images there, and you can also purchase access to some of our other audiobooks as well. But leave us a rating and a review on our app. We would really appreciate that. Chris, columnar joints. So we've talked about this on the podcast before. I can't even remember what episode. It was maybe St. Helens we were talking, or something like that. I don't remember when we discussed
No, I don't
jointing.
think so. I think it was Devil's Tower. It was Devil's Tower in Wyoming.
Right. Yeah. Okay, which is a famous one of the top couple places on the earth that have columnar jointing. But there's many places that have this kind of feature. So if you haven't seen columnar jointing, what we're talking about is often lava flows, basalt flows typically, but not always, that have this usually hexagonal six-sided column jointing pattern. So the rock breaks apart into these big six-sided columns, and they can be big. The columns themselves can be between centimeters to 3 meters wide. So they can be big blocks
and
of
even
rock.
bigger than that. Yeah. Devil's Tower has columnar joints that are much larger than 3 meters across. So they can be unbelievably huge. Yeah.
Big columns that are called columnar jointing. And it's jointing, so the rock is all the same. It's a jointing pattern in the rock. These are breaks in the rock that create these columns. So they run either vertically, or Chris, you said, so you saw some horizontally. We also saw some together. We're going way back now. A couple different places, but I think we saw some in Colorado, and we saw some in the Columbia River Gorge was the main place we've seen the spectacular columnar jointing in the Columbia River flood basalts there. So there's many places to see these things, I think is my point. But that's what we're describing. Columns that are, the rock is fracturing in this columnar pattern, hence the name columnar jointing. So Chris, when you're standing there in Iceland, you and Jenny, and you're like thinking about this as if you were not a geologist, or if you've never thought about columnar jointing, what are the main questions do you think that, I don't know, entry-level student or somebody who's there and has not thought about geology, what are they asking themselves, you think, looking at these columns? Because, these are these are mystical features, right? There's all sorts of stories from going back to indigenous communities with Devil's Tower and Devil's Postpile where they had stories about how these formed. They're kind of mystical features. So you could come up with some wild ideas about how they formed. What do you think the average person's thinking?
Well, this is purely my own thoughts. Actually, not really, though, because Jenny is standing right next to me as we're looking at these very diverse columnar joints in Iceland. And so this kind of comes from some of the questions she was asking. And so I don't know, it's kind of like a combination of questions Jenny asked and me wondering, you can't mistake this pattern that you see right in front of you. I mean, you look at that, you're like, wow, what is that?
One quick interruption. I mean, Jenny's not a normal human, so let's not say that, this isn't her perspective is coming from a normal human. But with that caveat, that's what is she wondering?
So why are they six-sided? That's a question.
Okay.
First of all, like an overview of how do these columns form? That's a question.
Which are kind of related, those two, I would say. The answer, at least, is kind of related, right? Yeah.
Yes. And then we saw a huge diversity in terms of like the diameter of the columns. Some were quite small. You could almost palm the columns, and some were, a couple of meters across.
Oh, right.
So
okay.
What determines the size of the columns? And then why don't all lava flows, if you have just basalt, which is what you have a dominance of basalt in Iceland, why don't all the flows have columns then? Why don't they all have this columnar jointing?
Okay, that's a good one. Yeah, that's a good one.
And then lastly, you have columns that are straight up and down. You have columns that are almost like horizontal. And then you have columns that kind of look like a pinwheel, or they form this kind of fanning out pattern from a central point. So why do you get these irregularities in columns?
Yeah.
And I think that's where I left it in terms of the questions that people would want to have answered if they're sitting there looking at them.
I think that's a great, series of questions. So again, it's just, so how did they form? Why are they six-sided? Those are kind of the same question in many ways. What determines the size? You said there's this huge range that you saw just in Iceland, and we've seen ranges. We've seen, I think, in a rhyolite, we've seen them sort of hand-sized, something along that size. Why don't all flows have columns? And then why the irregularities? Is that right? That's the last question. Why the fan structure? Why the horizontal ones? Why the vertical ones? Okay, cool. Should we start at the basics? Like, how do these things form and the sort of history of them then?
Yeah, let's go back up to the top and let's start with like this kind of, I think you have a better perspective on like the historical view of these things. And then let's just kind of take it in order. Does that sound good?
Absolutely. It's kind of one of these things in geology, one of the few, I would say, in geology, where there's been ideas for many, many centuries because they're such a strange phenomenon, right? You look at them and you're like, whoa, that is crazy. So people since the 1600s have been writing about these things. There's been many models over the years of how they formed, including little convection cells that were kind of, imagine a convection cell that would kind of spiral upwards. That was one idea. Another one suggested that they were crystallization patterns. So the magma started to form little balls and nucleate around them, little plastic balls as the magma was crystallizing that eventually formed columns. And this, if you go back to our interview with Mike Ackerson, he talked about the sort of early debates about how magmas formed, whether there was such a thing as magmas or not, this Neptunist versus Plutonist kind of model, and the columnar joints were kind of really involved in that debate. There was debate about how columnar joints formed. There is a widely accepted model.
Hold on, Jesse. Hold on. I gotta go back to something because you're dropping big words here, and like what is this Neptunist and Plutonist view? What does that mean?
Well, I don't think we need to get lost in the weeds. Mike Ackerson did a great job explaining it in that episode, but it was people who were debating.
We need to have Mike on again, by the way.
Yeah.
We need to get Mike back
columnar
on.
joints. Yeah, for sure. People debating going back centuries now, talking about how igneous rocks, what we think of now as igneous rocks, how did they form? There's kind of many schools of thought, and one of them was called the Neptunists and Plutonists. So if you're interested in that, I would say go back and listen to Mike Ackerson. The point of these columnar joints, though, is that we have a widely accepted model. It's a cooling feature, meaning the rock is hot. It's fully crystalline, so it's a crystallized rock, but it's hot, and it starts to cool down, and then these joints start to form. That's been around since 1776, Chris, so you might say it's an idea that's been around, that's as old as America itself. But it's...
I thought you were going to give a crack at me.
Oh, I should have. Man, I missed opportunity.
For my age.
I'm really out of practice.
Rusty.
I'm really rusty. Dang it. That was a big missed opportunity there. Bummer.
That's right. So I think what you're talking about is columns are going to start to think about forming when the rock turns from orange to black, let's say. So the flow has become stagnant. It's turning color now because it's going from lava now to crystalline rock. At that point, then it's still super hot. You wouldn't want to walk up and touch it, but it's no longer lava. The point where it's turned from orange to black.
Put a number on this. Basaltic rock is fully crystallized at about 800. I mean, it depends a lot on the composition, but we're talking 850 degrees centigrade here, 800 degrees. That's really, really hot. And then it's got to cool down to surface temperature. So there's a big interval of not crystallization, but cooling that happens here.
And then that begs the question, as this superheated rock continues to cool, what happens then? That's the question. And that's really like gets at the basics of why do these columns begin to develop. So as it cools, it's going to begin to contract. But remember, rock is not very elastic. It can't just change form. So what it's doing is as it's cooling, it's building up stress. Building up more stress, cools off more stress is built up because the rock is really contracting and kind of like pulling into a central point.
Yeah, shrinking. We have this big massive rock that's cooling and shrinking. And what's happening is we're forming tensional stress, what's called tension, pulling things apart, basically. It's kind of analogous to that. It's like the rock is being stretched apart, but it's not. It's just shrinking internally. Something's got to give. You said rock's not elastic, so something's got to give. It's going to break eventually. And there's a lot of people who've studied the physics of this stuff in detail, but basically this is where the six-sided nature comes in, or the most commonly six-sided nature. Now, nature is full of irregularities, so it's not always perfect six-sided columns. But Chris, I'm sure you saw some perfect six-sided columns, and then you saw some that were irregular as well, right? I'm guessing.
Yes. Yeah, absolutely. Yeah. In fact, just a real quick side note. I don't mean to distract you because I can see that you're on a roll here. But when we first got there and we had rented our car and we're driving and we see some columnar joints along the roadside, I was so excited. I'm like, well, let's pull off. And it was driving rain. It was just miserable. And I put my raincoat on, put my pants on. Jenny gets out there and we hike up to where we can like look at these things up close. And when I think about it later on, as the trip moves on, that was kind of a dumb thing because these columnar joints that we had first gotten so excited about were rather pathetic compared to all of the other ones that we saw as the trip moved on. I mean, they were old, they were crumbly, they just weren't very spectacular, but I was all excited because it was the first ones that I'd seen out of the country. So,
yeah, I mean, so cool.
I was happy.
Yeah, oh, of course you were. I mean, so cool. So these beautiful columns, they form by contraction. The rock is cooling down. It's going to break. Something's got to give. It's got to break. And the commonly six-sided nature of it is just to do with the physics of how you break a rock, or how, basically it's how can you put breaks in the rock with as few of breaks as possible that run through the rock and kind of make a nice mesh. And I think, Chris, you ever play the board game Settlers of Catan? Did you guys play that game as a family ever? No? Okay. Well, it's this board game that has
that I remember. No.
It was popular. I mean, it's still popular as people, but it was a fun board game that our family got into for a while. And it has these six-sided pieces. Board game that has six-sided pieces. You put it all together and it has these six-sided pieces. And that's just the most efficient way to fill a space with the fewest amount of sort of lines possible. And this is similar.
Can I give a crack at it? The math is very complicated. For something that is cracking this way, where the tensional stress of the contraction exceeds the strength of the rock itself, and so cracks will begin. Hexagonal shapes, it releases the greatest amount of energy along the shortest lines, I guess, along the shortest cracks. It's the most efficient way to break while releasing the greatest amount of energy.
So, Chris, when we talk about in sort of petrology terms, when we're looking at rocks and looking at minerals, there's the exact same thing happens when you crystallize a rock, or when you, in metamorphic geology, when you recrystallize a rock. When you put heat in there and the minerals are recrystallizing, it wants to be as energetically efficient as possible. And the way to minimize this free energy, what we call Gibbs free energy, is to have the least amount of grain boundary interactions. And the way to do that is to form what are called triple junctions, where you have three minerals that come together in a point. And so three minerals touching, they have these 120-degree angles in the minerals. And if you add that up, you get a six-sided thing. It's just the most energetically efficient way to either break a rock or recrystallize minerals in a rock. And this is all over nature. This six-sided thing is kind of all over the natural system because it is energetically most efficient way to do it. So the ideal, the perfect scenario is a lava flow that's cooled down so it's crystalline, it's fully crystalline, and it's sitting there. And it's a thick lava flow, so it's hot inside, quite hot. The surface is cooling down. Both, actually, the bottom and top surfaces are cooling down. And as those cool down, the top and bottom start to contract. The inside's still hot, so it's not contracted yet, but it's starting to. As the whole body cools down, these fracture networks kind of happen. And Chris, there's a good analogy here with mud cracks. When we look at mud cracks, where there's a muddy layer on the top and it starts to dry out, it shrinks, it desiccates out. It's doing the same thing, and the physics are very, very similar. The mud crack will form these six-sided mud cracks. That's like the energetically efficient way to do it, at least. Except in a basalt flow, the whole package is cooling. So it's not mud cracks, we get these little chips because the surface is the only one that's drying out. But in a basalt flow, the whole thing cools down. So you get these vertical columns, and they kind of propagate their way down into the lava flow itself and create these columns.
You touched on this, but I want to make sure that we double click on that. The columns are going to grow and propagate perpendicular to the cooling surface. So if you have a lava flow that then crystallizes, the cooling surface is the air. So it's relatively flat, right? And it's losing heat very efficiently to the air above it. And there's your cooling. And so that's where the cooling starts. And the columns then will propagate downward from that horizontal cooling surface, which in this case would be just the air.
That's exactly right. And we're going to come back to that point, Chris. I want to set that aside, set that on the shelf for a minute. We're going to come back to that in one of the later answers to one of the later questions. But remember that the top is cooling, but also the bottom is cooling. When this lava flow comes in, and this is a lava flow in this instance, the ground is cold too compared to the lava. So the top and bottom are cold, and the middle is the hot part. Let's leave that there for now and come back to that to answer one of the later questions. But Chris, the size. What determines the size of these things? You said you saw a variety of sizes. What range? What were the coolest ones maybe? Which ones do you like? The big ones or the little ones?
I like the little ones.
Oh, yeah? Okay.
I don't know. To me, they seemed to be more perfect. More idealistic, I guess. I'm getting excited thinking about this again because I'm reliving where I saw these things. And Iceland is so well known for all the waterfalls. Well, waterfalls and rivers, they cut gorges down through these old basaltic lava flows, right? Which exposes then the guts of the lava flow. So you can see a layer of columnar jointing, maybe 5 to 10 meters thick. And then down deeper below that, another layer of columnar jointing and so on and so on and so on. And it was just really, really cool. I liked the smaller ones.
Okay, interesting.
And they seem to be more perfect to me. That does beg the question, why do you have this diversity in terms of how big the columns are? Because Devil's Tower, several meters across, is not uncommon at all. Well, it turns out that the size of the columns is inversely related to the rate of cooling. So, in other words, if you have a lava flow that cools very fast, the columns will be small. Okay. If you have lava that cools really, really slow, the columns then are going to be much larger. So it's inversely related to rate of cooling.
And Chris, we actually read a paper that people had noticed in a chert layer, they'd found very, very tiny columns, really, really small millimeter kind of columns that you'd see under a microscope. I mean, you could see it with your naked eye too. The idea was that this chert layer had gotten heated and then cooled down really quickly by an ash layer that was kind of decomposing beneath it and dumping heat into this chert thing. So there's all sorts of different rocks that form this type of thing, and some of them can be really, really tiny. Those are fast cooling. The big ones are slower cooling. And the slower cooling, again, it's kind of this physics thing. The slower the cooling, the further away the joint sets can be from one another and still be energetically efficient.
That's right. And then your mind maybe thinks about, well, what would cause different cooling rates of, let's say, lava, right? Well, the geologic setting of a lava flow can affect the rate of cooling. For instance, if you have a lava flow that enters a gorge, you're going to have a relatively thick lava flow that is not very wide. It affects the rate of cooling, or maybe the chemistry of the lava flow itself, whether it's andesitic versus or mafic and basalt, that kind of thing can affect rate of cooling. And then other variables, maybe like the amount of vesicles or gas pockets that are in the lava, is going to affect the quality of the columnar jointing, and it's also going to affect the rate of cooling.
And I think, but probably, Chris, and I'm curious if you noticed a relationship here, the flow size, the thickness of a lava flow, would probably be a major component. Did you notice that the little perfect ones that you loved were in narrower or thinner flows, or not
yes.
really? Yeah. Okay.
Absolutely. I did. Yeah, absolutely.
And so if we go back to Devil's Tower, this huge, Devil's Tower is a huge slug of magma. A big basaltic intrusion has a lot of heat in it, and so it'll take longer to cool down. So that's why those are much bigger than some of the small ones you probably saw.
That's right. Because in the case of Devil's Tower, one of the leading theories is that this was an intrusion. Right. It was a shallower intrusion, but that means that the cooling surface was not air. And rock is an excellent insulator. So, in other words, if lava intrudes or magma intrudes country rock or rock around it, it's going to insulate it and cool much, much, much slower than if it was just exposed to the air, because it loses heat readily to the air.
And that's a great one, Chris, that I think we'll come back to again when we talk about some of the irregularities or irregular patterns. But let's talk about why. I think this is a nice transition to talk about why don't all flows have columns. And I think this is a interesting question that there's not a clear answer to, because if you think of a lava flow, it's eventually all lava flows are going to be solid, and they're still going to be hot at that point, and then they will be cooling down in this way. It's an interesting question. Why don't we see this more frequently? And I think the answer probably is that you need a really perfect or near perfect cooling setting to form columns that we can identify. These are really striking features, and they grab your eye when you see them, but you need to have a really nice, very kind of clean lava flow that is solidified and pretty thick, and then have a consistent cooling pattern after that in order to create these really nice columns. So anytime you have like a jumbly lava flow or a thin lava flow, is very unlikely to probably form these columns because it cools down too quickly to form this. It probably flowed in the top, crystallized, we formed or Pohoi, lava on top, and then it got jumbled into the mix. So you have this irregular cooling pattern as the lava is flowing downhill, and then therefore it's not a big, thick, 10-meter thick package that's consistently cooling from the top down. It's kind of a mix, and there's little convection cells, and it's doing all this other stuff. Maybe there's a lot of vesicles. So that would disrupt the physics of this column forming jointing process. Those are some reasons why not all lava flows would have this. And relatively thin ones are often ones that don't have this process. You need a big batch of lava that cools down and is cool and solidifies in place, and then cools from there to surface temperature consistently and in a stable way.
Because if you mentioned Pohoi is it's one of my favorite flow textures that you can get in a basaltic rock. But it's exactly that this texture that you get with Pohoi, it's kind of this smooth, ropey or twisted kind of braided appearance. You can actually see the flow of the lava that's preserved in the rock. When you look at that and you hold that in your hand, that kind of flow texture is going to disrupt any kind of columnar jointing that would have happened. It has to be a rather stationary flow. So lava flowed, stopped, solidified, and then columnar jointing took place after the material turned from orange to black.
Yeah.
But
that's right.
I have a question for you, Jesse. Then I'm gonna throw this at you, and you don't know what I'm gonna ask. So let's see how you do.
Okay. All right.
So we saw this. Okay, we saw relatively thin layer of columnar jointing, but the columnar joints were horizontal. What do you make of that?
Meaning the joints were running horizontally. Is that what you mean?
Yeah, they were not vertical columns. These were horizontal.
So this, I think, Chris, leads very nicely into the last question. Like, how do you get these irregular patterns? You talked about these fan-shaped ones. The horizontal ones are, I would say, irregular. They're not the normal pattern. And the physics here, I think, are just exactly the same. Jointing has to be perpendicular to the cool side. So if you imagine a fan, what does that tell us? A fan, where the joints are kind of fanning outwards, that tells us that all sides were cool. The flow punched into like a sediment, or it punched into something where it cooled consistently from the outside. Imagine like a plug of magma kind of bulging out into a sediment package, and then it's cool on all sides of that, and it starts to cool radially inwards. And the joint sets will be perpendicular to the cool surface and then come back in. So that's one way. So then horizontal, this is quite common in cooling lava, is that eventually as the top cools, it'll crack, right? And those cracks will allow water to get down in. And you can get these big water circulation paths, which the water is a great cooling element. And so if you have a crack that's going vertically down and the rock is still hot, but that cold water is circulating, it's cooling down horizontally. So you can get horizontal joints that come off from that hydrothermal water crack, basically.
Exactly. That's one way. In the case that I'm thinking of specifically in my head is the difference between a sill and a dike, the geologic setting.
Right.
Okay. So sills are these igneous intrusions that run parallel to the rocks it intrudes. They tend to be more horizontal. And so with that kind of intrusion, where it's like a relatively flat horizontal layer, the cooling surface is the rock above it and the rock below it. And so you're going to get vertical columns. But a dike cuts across the rock layers, often vertically across it. And so the cooling surface is now on the sides. And so you get these columns that extend and they look more horizontal. So that's another way that you can get this kind of irregular pattern to it.
Okay. Yeah, I like that.
I don't know. My favorite thing though, Jesse, were these kind of what I described as pinwheel, or kind of this radiating out from a central point columnar joints. Those, I've never seen them before in real life. Have you ever seen this or not? Like firsthand, have you seen that?
Not the full circle. We saw like half circles in the Columbia River Gorge with our buddy Andy. But
okay.
I've not seen the full circle.
It's something that it's got a name. It's called entablature. These kinds of columns that have this irregular fanning kind of appearance. And you're right. This is a different geologic setting. And it often involves the interaction with lava or magma and water. And in the case of Iceland, what you would have are these lava flows, and then you'd have a sudden, like a flooding event, and the water would interact with the lava flow and affected its cooling and its cooling rate and its cooling direction, which kind of formed this kind of pinwheel look to it. Does that make sense?
Yeah, no, absolutely.
I'm kind of describing?
Absolutely. And just to touch on that entablature word that you just said, the sort of textbook example of this is if you have a really thick flow, the top will have beautiful columnar joints patterns that are vertically stacked, and then we call these like colonnades. So the top and the bottom, remember the bottom is a cooling surface as well. So those will form this kind of sandwich of colonnades, these beautiful, perfect ones. And then inside, you'll have this kind of irregular pattern, this entablature. And that's where the top cracked and you got water circulating down. And it started to get more complicated down in the middle part as the entire package started to cool. And I saw, Chris, the most spectacular columnar joints I've ever seen was a really, really thick lava flow. It's on what's called the east arm of the Great Slave Lake up in the Northwest Territories of Canada. It's this huge basalt flow formed this big cliff. And so we're flying in a helicopter over the lake, but right next to this cliff. And it's just huge columnar colonnades with this entablature thing down near the water's surface. It was spectacular. Like looking out the helicopter window, it's just just one of those like surreal moments where you're like, what the hell am I doing here? Like, this is crazy. Flying over this ultra deep lake, this huge amazing geological phenomenon to the left side. It was just so cool. And I think our helicopter pilot got a kick out of it too, because he's flying next to the cliff. You know, it's kind of fun.
So is that your first and only time of seeing that kind of entablature look to columnar joints?
Seeing it like that in that textbook way, where it's like colonnades on top and on top, you know, that was the first time seeing, like, I mean, you and I saw them just after I graduated college. We saw the complicated, pinwheels and fans and stuff, but the full package of entablature, that was the best time I've seen it for sure. Let me just summarize this again, Chris. The irregular patterns, the non-vertical patterns, the physics are the same. It just points to a different cooling direction or a more complicated cooling pattern in the columnar jointed basalt or lava flow or whatever the thing is that's being jointed. So the physics are the same. Cooling pattern is perpendicular to the jointing, and so it just points to some different cooling pattern. Chris, maybe to wrap up, I have a question for you. Where are the closest columnar joints to you right now in Hudsonville, Michigan? I don't know. I'm asking. I don't have an answer.
Boy, I don't know for sure. I probably say Devil's Tower. I think.
Okay. I didn't know if there's any up in the Upper Peninsula at all in any of the.
No, I don't.
The basalts.
I have not seen columnar jointing there. Lots of pillows.
Yeah.
Which are really cool structures too. And, you know, we saw some pillows in Iceland as well. And I'm a huge fan of pillow lavas. The story that rock has to tell is just, I don't know.
Oh yeah. Don't get distracted.
So
don't get distracted by that. Yeah, that's a whole nother thing. Okay. That's interesting. I mean, because Yellowstone, there's a lot of places out west that have them. Yellowstone rhyolites have them. I think the closest to me is Shenandoah National Park. Has some good ones there out there in Virginia.
Okay, I guess that would be closer to me too. Yeah.
Oh, is that?
I didn't know that.
Yeah.
I didn't know Shenandoah has that.
They've got some good ones. If I remember correctly, it's like a few outcrops that have like a roof overhang, so the columns are kind of over your head in some ways too. They're pretty big ones, but they're 550 million year old basalt package there.
So can I tell you a story about Iceland real quick here that's relevant
absolutely.
to the discussion? So there is a famous outcrop right along the ocean. It's a black sand beach Then you have just these beautiful columns. This is hilarious, Jesse. It made my whole day. So first of all, I was a little pissed when we got there because you had to pay to park there. Okay. And I'm not happy about that. But, I'm like, well, it's so famous an outcrop that I have to go. I'd never been there before. I don't know if I'll ever be back. I have to go. So we get there and I'm like, oh man, this was a waste. Because the columns are cool, but they are not cool like the columns we saw in the backcountry or all over the place in other places where we saw them for free, right? But I had to do it anyway. So Jenny wants to get this picture of me sitting on a column. And so I get to this column and it's busy. People are everywhere, which that didn't, lighten my mood either. I was like, we'd spent so much time like alone and away from everybody. It was spectacular.
And also you're turning into a bit of a hermit loner in your old age too, I think.
I know, but this Jesse is the best. So Jenny is trying to get a picture of me and she's trying to like crop everybody else out of it. Right. And I'm like, Jenny, hurry up, because there's the ocean. There was this rogue wave and it was just crashing towards. So Jenny has her back to the ocean. I'm looking at it and I just waited until the last possible second. I jumped off the column and I just ran as fast as I could. Jenny soaked up to her knees. It was just the best.
That's good.
It couldn't happen to anybody nicer.
No,
and you know that because you know Jenny so well. So
nobody deserves to get soaked up to their knees while trying to take a photo of their husband more than Jenny Bolhuis. That is the best. And what a great way to experience columnar basalts is just, having Jenny take a photo and getting soaked.
Yes.
That's great. That makes me very happy.
Oh my gosh. She was so mad and I was so happy. I'm like, this was worth every penny we spent to park here because you got absolutely demolished by a wave. It was
I want to see the photo. I want to see the photo series of, you looking, hurry up, Jenny, sprinting away, the time lapse. That'd be great.
I don't know if she got me jumping off the column, but I'll certainly send those. I think there are 2 pictures that she managed to take. And it's so funny too, because she's notoriously like it takes her a long time to take a picture. It cost her here.
Cost her big time. Cost her dearly.
The time.
Yeah.
It was so good.
Serves her right. Serves her
worth
right.
every penny.
That's great. Well, Chris, I think this is probably the first of many of a sort of a Iceland, or let's say our summer trips inspired podcast episodes. I've got a couple too that I'll pitch your way based on stuff we did. But yeah, I think that's probably a wrap on columnar jointing. We hit the basics. There's a lot to know. And I think one other thing I would like to touch on, Chris, is that people have studied this a lot, the physics of this. And they do both experiments like starch. They can do it with a starch slurry.
Yeah, no, that's crazy, isn't it?
Yeah, kind of cool, right? It'll cool down, it'll dry out, and you can form columnar joints. I didn't look it up. There must be like you could do this at home, I'm guessing. You could replicate this experiment at home and form columnar joints in a starch. I don't know what the recipe is. Maybe we'll have to find somebody on YouTube must have done it at some point.
It looked like fun. Totally. The columnar joints in that starch was really cool.
Really cool.
I got to figure out a way to do this.
Maybe that's an exercise we should do in your intro to geology class, Chris, and do that as a lab.
I think you're right.
At some point.
Actually.
That'd be kind of fun. Do that this semester and let us know how it goes. That'd be cool.
Okay.
But people have studied
I'm actually going to do it.
It's cool. There's a lot of different ways to understand the physics, and these things are kind of everywhere. This hexagonal shape is sort of just a fundamental natural phenomenon. So it's kind of cool.
Before we exit out of this, I just want to say to our listeners that if you have questions that we didn't answer about columnar joints, send them our way and we can maybe tack this on to another episode. If we skimmed over something that you didn't maybe understand, or you have a different question that would pop into your head as you were looking at columnar joints, send it our way.
Yeah, absolutely. And those of you who have sent us questions, we've aggregated them all. We've gotten a lot this summer. We appreciate it, and we're getting to them. Let's put it that way. We're working our way through the question list for episodes here. So if you don't hear it, the next couple weeks, that's okay. It's still probably coming. An answer's probably coming your way, and we appreciate the questions. If you're looking to support our podcast, you can do that 2 ways. You can head over to our mobile app. You can download the mobile app. It's the Camp Geo mobile app. First link in your show notes. There we have a bunch of stuff for sale. We have basically the entire Intro to Geology course for free as well if you want to listen to that. It's audiobooks with images. We think the images are, particularly for geology, really important and really add something to the listening experience. So we've been producing those. We continue to produce more in the background here that we're working on. Head over to our Camp Geo app. Leave us a rating and a review if you do that. You can also head to our website. There's a support us link at our website, planetgeocast.com, that you can support us there. We always appreciate it. And like Chris said, send us an email, planetgeocast@gmail.com. Thanks.
Cheers.